Hello everybody, thanks for coming. My name is Timur Doumler. I'm going to talk today about C++ and safety. Just a disclaimer, I literally put together the slides for this earlier today. I haven't rehearsed it at all, so it's a bit rough. Please feel free to interrupt me if there's anything wrong, or you don't understand anything, or you think I'm just not saying the right thing or something like that, or if you have questions, please feel free to interrupt me. So why am I talking about safety? I'm not even a safety expert. Well, I had the idea in December to just write on Twitter, hey, does anybody have any ideas about what I should be talking about? And then my friend JF Bastian said, well, why don't you talk about safety and security in C++? And I think he meant it as a joke, but my brain doesn't really pass jokes very well, so I just thought, yeah, that's a good idea. So I ended up actually writing a talk about safety, and I ended up submitting it to this awesome conference that, as Bjorn already mentioned, it's awesome. Go there. It's at the end of June in Folkestone in England at the coast. And yeah, it got accepted there, so I guess I'm actually giving this talk. So yeah, let's see how that goes. So I have a first kind of very rough draft version of this today. As I said, feel free to interrupt me, give me feedback, ask me questions. But why safety? So what happened? So depending on how much you followed kind of C++ social media over the last year or so, you might or might not know that there has been a little bit of kind of a large amount of different documents and reports coming out addressing safety concerns in C and C++. So, for example, the NSA, which we all know and love, this is, I think, from November last year, said that, well, exploitable software vulnerabilities are frequently based on memory issues, things like overflowing a memory buffer and like use after free. And Microsoft and Google revealed that about 70% of the vulnerabilities that we're seeing were due to some kind of these kinds of memory issues. And the problem are commonly used languages such as C and C++, which are not memory safe. And so we should not be using them anymore, and the NSA recommends that we should be using memory safe languages instead. And actually the whole community should just move away from C and C++ and use memory safe languages instead. Yeah? So then there was another report from the National Institute of Standards and Technology, which is another US government body. It's from the US Department of Commerce, who was saying very similar things in that report. And it's not just the Americans now, because a couple of months ago the EU now also started getting involved in this. And so the EU is now drafting a Cyber Resilience Act, where they're proposing regulation in some kind of standard that they haven't written yet, as far as I know, but presumably are writing as we speak, about cybersecurity requirements that apply not only to safety critical code, but to all software, as far as I understand. How we should write code with memory safe languages and in a way that doesn't allow for memory unsafe code and vulnerabilities resulting from that. So there's a lot going on there. It's also not just government actors. There is this Consumer Reports report here that was also quite widely cited. That's from January this year. And they're saying... Yeah?
Do they define security?
We're going to talk about that in detail. And this is... yes, we're going to talk about what safety and security means. Yes. So this Consumer Report... also finds that roughly 70% of browser and kernel vulnerabilities, so it's not just Microsoft and Google now, are due to memory unsafety, and many of which can be solved by using memory safe languages. And so they're also calling for the whole industry to shift and basically moving off C and C++. And we're not moving off C and C++ because we have fallen prey to the sunk cost fallacy, and we need to be convinced to just stop using C++. And everything's going to be better, and it's also going to result in higher productivity. So, and it's also going to be cheaper, and everything's going to be great. Well, and so that set off kind of a bit of an avalanche of, related publicity. Here's just an example of an article that also came out recently, and there's been so many of them over the last year. I don't know if you followed this or not, but this is kind of the hot topic right now. Of course, the question is, should we care? Like, do we care about what the US government said and some random other websites say? Well, it depends. So certain people that I very much respect, for example, Bjarne Stroustrup, the creator of C++, or J.F. Bastian, who is the chair of the evolution study group on the committee, which is the group that is responsible for designing the language, they're all saying that this is an existential threat to C++, and they're being very serious about it. Right? This is not a joke. On the other hand, I also heard a lot of people say, well, we don't really care. And to be honest, for most of my career, I have been very much also on the right-hand side of the spectrum. So I started doing kind of scientific software where we were running these astrophysics simulations, and if they crash, well, it's not great. You have to restart, but nobody really cared about them being hacked or anything like this. Then I was doing audio software where, you kind of care about them being hacked primarily because people will want to circumvent your copy protection so they can get your plugins for free. But again, it's not really a security concern necessarily beyond that. And so it seems like it really depends on kind of what industry you're in. And there are these very heavily regulated industries which do safety critical software where there's human lives on the line if something goes wrong, right? Automotive, medical, aerospace, civil engineering, and others. And there are some industries where maybe, I don't know, we have some gaming people in the room. Of course, if you get a glitch somewhere, it's not nice. Somebody might notice, but the world is probably not going to end if that's going to happen, right? Yeah. So it seems like it really depends on where you are on the spectrum. But also, if you are on the right-hand side of the spectrum, there are a few other concerns. So even if you write software that is not seemingly safety critical in the sense that if it crashes, somebody's going to die, let's say things like, I don't know, Acrobat Reader or, some popular word processor or things like that. Things like a lot of people have on their laptops. Well, it seems like that's a factor too. If millions of people have that software, or half of the people in the room have that software running, then all of a sudden it does become an interesting target for vulnerabilities, even though it's not, in a safety critical industry. And also it depends who the users are. If it's software that, is used by a significant amount of governments, for example, they're a very attractive target for certain types of hackers, right? So, yeah, it's kind of it seems like there are maybe more pieces of software than we think for whom this would be, a very important concern. And so we have to ask ourselves, okay, so what's going to happen? There's all this noise, right? But what is going to happen? And it seems like it's very likely or almost inevitable that there's actually going to be some kind of regulation around this, right? Then, we can ask ourselves, who is behind this? It seems like it's mostly governments and security experts who are working, for those government agencies. So what do they want? I don't know, but you can be optimistic and think that they just want our games not to crash and things like that, right? I do have another theory. I don't want to go too deep into conspiracy theories and things like that, but obviously governments care about the infrastructure. And a lot of infrastructure isn't regulated in the sense that automotive or aerospace is, and they use all kinds of code from everywhere, like Boost or whatever, right? And so it seems like there is this movement to kind of shift the responsibility of C and C++ code to not have vulnerabilities onto the wider software industry to kind of protect maybe our infrastructure or other things, right? I don't know. I don't want to go too deep into this. But Are they right? Should we abandon C and C++? That's the real question, isn't it? And it's kind of yes or no, I don't know. But like certain things are kind of facts, undeniable facts, right? So the thing that 70% of vulnerabilities roughly are due to memory safety issues that occur in C and C++ and are not possible in certain other languages, that's a fact, right? So we could say, yes, maybe it is a good idea to move away from memory unsafe languages. But, so something that I noticed in all of these reports and all of these news articles and all of that is that they always talk about C/C++ as if it was the same language. Well, if you look at it a little bit more closely, it's actually not quite the same language. And so indeed C is quite notorious for having probably more vulnerabilities than most other languages. C++, on the other hand, is by the metric of like how many vulnerabilities we're seeing, certainly a lot safer, and also safer by this particular metric than some languages like Java, which are considered memory safe. And so, of course, C has lots of unsafe features for which C++ offers safer alternatives, right? So we don't have to deal with void pointers. We have variant in any. We don't have to deal with raw char pointer strings. We have string. We have variant, which is a safe version of union, right? We don't have to deal with function pointers. We don't have to deal with naked arrays or maybe dynamic arrays, or instead of a pointer of a size, we can now pass a span. We have exceptions. So pretty much all of these things on the right are still not 100% safe, right? So you can index into a vector out of bounds and get undefined behavior. You can have a function and you don't initialize it, and then if you call it, it's also undefined behavior. But arguably those things on the right are safer to, it's a lot easier to use them safely than to use row C. And also something that's notable is that actually a lot of the languages or actually all programming languages have a very significant amount of vulnerabilities. It's just like where they are. So if you look at vulnerabilities in Rust, this is just a screenshot. It's a much longer list than that. They have a lot of vulnerabilities too, right? It's just not something like use after free. It's typically either something where in a standard library or somewhere else or in some other library, there is a piece of unsafe code somewhere, or it calls into some non-Rust code, or there are other types of vulnerabilities. So all programming languages have vulnerabilities. The question is just where are they? There isn't such a thing as a safe language, and it's just not about the language. So we're talking about programming languages, but there's like a whole stack, right? So if you have a programming language, underneath there is some kind of system, right? So in the case of Java or maybe a dynamic language, it's some kind of interpreter, or Java, the Java virtual machine, or there's maybe a compiler. Then it runs on an operating system, which runs on hardware, and then at the other end we have the environment, right? We're calling out to servers and the internet and things like that, right? So all of these things can bring in vulnerabilities. So Rust has vulnerabilities that we saw. Java has vulnerabilities, the famous log4j thing that was going on. And then we have things like Spectrum Meltdown, which are, basically hardware vulnerabilities, and they don't even depend really on the programming language that you're using, right? So it seems like we have this ocean of vulnerabilities, and if you try to stamp out the ones that have to do with particular memory safety in C++, then the attackers are just gonna shift to something else, and they're gonna find vulnerabilities in other parts of our stack, right? So it's a little bit like attackers they're like a gas, right? They fill whatever volume you give them. So if you close off something, they're gonna go somewhere else. And so it's not really about safe code or removing vulnerabilities. It's about reducing them. It's a little bit like the introduction of the seatbelt, which I believe has been invented by a car maker from this country. It's not about making sure people don't die in car crashes anymore, because they do. It's just about reducing the number of these car crashes, right? And you can spend more and more money and resources on this and be more and more safe. And if you have like infinite resources, you can get very, very good at preventing car accidents, right? You can have like the most heavily armored car in the world and have it surrounded by 20 other very heavily armored cars. And then probably, your probability of dying in a car crash is pretty low. It's still not zero, but the vast majority of developers and companies making software is not going to have these kinds of resources, right? So we are left with the question, should we introduce seatbelts to reduce the amount of accidents by some degree? And at what cost? And so in order to understand that, we need to understand the trade-offs. In order to understand the trade-offs, we need to understand what this is all about. And so there are these buzzwords, right? Safety, security, correctness. And it feels like before we can really reason about this, we need to understand what they mean. So on the C++ committee, we now have a study group concerned with safety. And they have published a definition of safety. They're saying that safety is an emergent property of systems measured statistically and regulated by policy. And the prerogative to decide if something is safe is usually reserved by governmental organizations. So this is all about regulation, and it's about certification. But actually, the important bit here is that safety is a property of systems, not of programs or a piece of code. We can zoom in a little bit, and there's this concept of functional safety. It's a kind of very long definition, but basically it boils down to, if you have a system that's designed to do something, to perform a function, then functional safety is if you take measures to make sure that that thing doesn't cause anything bad, doesn't cause any harm, any damage, etc., etc. So if you dig deeper into this, there's a lot of regulation around this in safety-critical applications like cars, automotive, medical, etc., aerospace. So we can distinguish hazards due to internal and external causes, and then one of the possible external causes misuse, and then that can be intentional or unintentional. And if you talk about intentional misuse, this is security, right? This is the difference between safety and security. So safety is kind of about something goes wrong because of a defect in the system or because of some external factor, unintentional external factor, like something unexpected happens. Can your system react to it without causing harm, right? And so that's all safety, and then security is about somebody trying to cause intentional harm. So if you want to know more about how people who work in these safety-critical applications, and I'm sure some of you actually do work in these industries, so maybe these acronyms are actually familiar to you. We had a CVPcast episode recently about this, where Andreas, who works at Woven by Toyota, actually joined us and talked in length about this. But we are at a C++ meetup, so we're not going to talk about systems. We want to talk about, of course, our favorite programming language. And so then we can zoom in a lot more and talk about a programming language being safe. But I wouldn't want to just use the word safe, because I think it has all these different meanings. So I want to be a little bit more precise and call it language safety. And so one definition of language safety, which I think is quite useful in the context of C++, this is a definition that Dave Abrahams, for example, used, is that a programming language can be considered safe if it has no undefined behavior. Right? So that's a useful definition, right? If a language doesn't have any undefined behavior, you can reason about what it's going to do. And that allows you to design your system or your program in a way that is safe. And so, yes?
It has to do also with the compiler. It's not only the language.
Yes, so the language, they go hand in hand. The comment was that it also has to go with the compiler, yes. So the language specification says that something is undefined behavior, but then of course that's there so that the compiler can assume that it's never going to happen, and then optimize based on the assumption that it's never going to happen. And that's the way you get performance, right? But then if it does happen, then the compiler has already optimized the code based on the assumption that it doesn't, and then you get weird results. So kind of undefined behavior, and you're right, compiler, optimizing compilers, they kind of go hand in hand. It's like two sides of the same coin. That's an interesting topic. This is like a whole talk in itself, like UB. There are actually a couple talks about UB, which are very good. But I want to briefly also touch on another buzzword here, which is correctness. And so what's correctness? It's not quite the same thing, right? So one definition is correctness is the state of being free from error. Well, okay, yes, that's correct, but okay. So the more useful term, and I really like to not use these blanket terms like safety, correctness, security, but be more precise and say what we mean. And so one slightly more useful term is functional correctness. So we can say that a program is functionally correct with respect to a specification. That's really important. Correctness is always with respect to some spec, right? And a program is correct, relative to a spec, if for every input it produces the output that satisfies that spec. Okay. Then of course the problem is, what's the spec? And sometimes that's easy, but a lot of the time it's very difficult. So there is this brilliant talk by Marshall Clough. It's the midpoint. How hard can it be? I really recommend you check out this talk. It's delightful. He talks for an hour about how to implement this. So it's a function. It's a function that takes two numbers and gives you the number in the middle, right? And so, is this correct?
The spec is easy though.
Well, so it depends on the spec, right? So for example, does the spec say what happens for integers if there's overflow? Maybe it doesn't. For floating point numbers, does the spec say what happens with different rounding modes? Do you specify that or not, right? Things like that. So watch this talk. It's great. Basically, by the end, he has an implementation that is correct with respect to some specification. It's very, very, very long. And it turns out that figuring out the spec is basically just as hard as actually implementing it. It's kind of the same thing, right? So one problem with correctness is that a lot of the time, the spec is incomplete. But even if we have a complete specification, we run into another problem, which is it's undecidable whether a program is correct because we have the halting problem, right? We can't even decide if a function returns in general. So we can kind of divide this further. We can say there is this concept total correctness, which means it returns the correct value, which is undecidable in general. But then we can also introduce this partial correctness. You can kind of factor out the halting problem and say, well, we don't know if it returns, but if it does, it always returns the correct value. And that you can actually reason about. There is Hoare logic, and if you're into computer science and maths and all of that stuff, there are formalisms to reason about this stuff, which are interesting. But for me as a practical engineer, I would say for any program of sufficient complexity, they're probably not going to be actually helpful in trying to figure out if a program is correct. So correct, yes.
What if the specification actually says that the output should be undefined behavior? Then it fulfills this condition of total correctness.
Yes, so if you say...
Perhaps lacking any kind of meaning.
Yes, so if you say the behavior is undefined, if the number is negative, then you don't say anything about what happens, and then the program is correct, even if it exhibits UB. That is absolutely correct.
So
yes.
The slogan total correctness sounds very
yes.
safe.
Yes.
We have solved the problem.
Yes. So we can have functions that are kind of, I don't know what the math term is. It's incomplete, where like they don't cover the whole domain of possible values that you can pass in, and then you have. It's a bigger topic, but yes, you can have functions that are not defined over all the values of a certain type, right? For certain values, they're undefined, and so the spec doesn't say what they should do. So we have this concept of safety, or we have these different concepts of safety, and we can talk about security, which is basically you can't hack it, you can't use it for malicious purposes, and so it seems like there's some kind of overlap there, right? You can say, well, maybe a program is safe, but it's not secure. Like, it's not going to crash, but it transmits your password in plain text, so that's not secure. But it's safe, right? It's not going to do anything bad to your computer in that moment. You could also argue, well, something can be maybe secure but not safe, like a program that always crashes but never exposes any personal data can be said to be secure but not safe. Maybe. But there is another definition. So for example, JF says that there's no functional safety without security. So he says one is a subset of the other. It kind of really depends on the exact definition. And then also here in the middle is this like very elusive, potentially empty set of actually correct programs. So it seems like reasoning about this is difficult, but again, we're at a C++ meetup, so what we can reason about is language safety. We can say if something has UB or doesn't have UB, right? And so, then we can talk about language safety and different kinds of language safety, and then it gets kind of more into these terms that are actually mentioned in these reports, right? We can talk about memory safety and thread safety and arithmetic safety, and there's a few other safeties which I'll mention at the end. And memory safety, can be further decomposed into type safety, bound safety, lifetime safety, and initialization safety. And so it seems that programs that are language safe in the sense that not having UB seems to be a necessary but not sufficient condition for all these other properties like safe and secure and correct, right? So you know that a correct program or a safe program doesn't have UB, or a secure program doesn't have UB, but it doesn't mean that if a program doesn't have UB, it's automatically safe or secure or correct, right? So here's an example of a program that doesn't have any UB, right? So we have this kind of accumulation operation where we have a float and we just keep adding 1 to the float, like 100 million times. What is this program going to print? It's a good question, isn't it?
50 million, I think.
There's no UB, right? There's no overflow or anything like that. It's floats.
But is it ever going to terminate? Yeah.
Yes, it is going to terminate after 100 million iterations, and it's going to print a number.
It's going to be stuck when the float multisabits runs out, and it adds to a number that only rounds to 2, so it's going to stop at that number.
So you would want that it prints 1 to the 8th, right? That's what you want. Unfortunately, it prints a number that's a lot lower than that, almost an order of magnitude lower than that. And the reason is that at some point you start adding very small numbers to very big numbers, right? And so you have this problem of floating point precision not being sufficient to actually represent the difference. And then you print a lower number because you're losing the precision, right, gradually. And so there is an algorithm with which you can compensate for this called Cahan summation, but if the person who wrote this code doesn't know that, they're going to get a completely wrong result. And that can have really bad consequences. Like I heard a story about, somebody programming a missile who was supposed to fly somewhere and explode somewhere. But then because of accumulating floating point errors, it exploded somewhere entirely different and killed innocent people, right? And that is a program that doesn't have UB, doesn't have any obvious vulnerabilities. It's just incorrect. It's like a logic error because the person didn't know how floating point math works. And so that's the kind of stuff that will happen in any programming language. So that is not really a problem, I think, specific to C++ in any way. But there.
Is the program incorrect? The floating point, it's well defined.
Well, yeah, it is well defined. Yes. So it is well defined. It is incorrect because you don't get the correct result, right?
Well, maybe that's the result you wanted.
Maybe that is the result you wanted. Yes. So we see that with something like unsigned overflow, right? Unsigned overflow is defined behavior, unlike signed overflow. And sometimes there are algorithms that exploit that, right? Where it's useful to have signed overflow, unsigned overflow. Other algorithms, it's a bug. Somebody overlooked it, and then that can have bad consequences. And you can't really tell. Yes, it is a logic error. It's not inherent to the programming language at all. I mean, here it's inherent to properties of IEEE floats, but it could be something else, right? So let's move on because I have lots of slides. Yeah, quick question.
I don't think the C++ standard defines that floats would give you that result necessarily.
No,
if you
no.
wanted that result, it will still be a bug.
Okay, yes. So assuming IEEE, this is what you get. And in some scenarios, this is going to be not what you want. And in some scenarios, this can have very bad consequences, right? But it has nothing to do with the language. There is no UB here. Okay, so.
Can I ask a short one?
Yes.
If I, as a programmer, get surprised, I mean, I don't know the intricacy of this behavior. I read the code and I think, oh, this looks fine. How do you deal with that kind of unsafety? Is that another level I mean, the language does, it looks to me as a programmer as it's correct, but it's not.
It feels like you're basically asking, how do we prevent bugs? That's a good question.
Writing tests.
I mean,
You can write tests, yes, that's a very good answer. A very good answer is you can write tests. Right, so it's not a sufficient condition to like have all of these safeties, but it seems like it's a necessary condition, right? And so all of these things, there's this brilliant talk by Jim Radigan from Microsoft from last year's CPPCon. He's looking at the top 25 most dangerous software weaknesses, and a lot of them have to do with exactly those things, right? Out of bounds write, use after free, etc., etc., etc. And so we can look at those and we can think about ways to ensure that we have these safeties, but they also come with trade-offs, right? So there's a trade-off between safety and correctness sometimes, or performance, or backwards compatibility, or complexity, or expressivity of the language. So we have to keep all of these into account. So let me just briefly kind of run through these just to make sure that we are all on the same page of what they mean, because I think this is kind of something that's important in this debate, that we all know what these terms mean and we're all on the same page about what we're talking about. So memory safety, actually, depending on the definition, might or might not include thread safety. So there is this paper which has a very rigorous mathematical definition of memory safety, which I personally don't think is very practical, but it's, I think, intellectually very interesting. And they actually include thread safety into their definition, but most people, they don't. When they talk about memory safety, they don't mean thread safety. So we have type safety, right? Type safety is the extent to which a programming language prevents type errors, that is, attempts to perform operations on values that are not of the appropriate data type. And here's my favorite example. So you have a struct widget, which has a function, and then you have a completely unrelated struct gizmo, right? They don't have any common base class or anything like that. And then you cast the gizmo to a widget, which you can do. It's a C-cast. It's undefined behavior, but it's going to compile and run, and it's going to do something. Question, what is it going to do?
Most likely it's going to call the other function because it's going to
Right.
have the same layout.
So on Clang, it's going to call the other function because it has the same layout. On GCC, the compiler sees that you've done an illegal cast and says, well, this can never happen, and it optimizes away basically all code paths that lead to that line of code, which in this case is the whole program. Okay, so here's another example. This is famous algorithm from the 90s, Quake 3. Gaming people will know this. Very fast way to approximate 1 over square root, which you need a lot in 3D geometry. Again, we're casting floats to ints and then ints to floats, which is undefined behavior. We do actually now, since C++ 20, have a type-safe way of doing this using bitcast, which incidentally compiles down to the exact same code, but is not undefined behavior. So please use that one. I did a talk basically 3 years ago about just this, type punning and this kind of stuff. So we have bound safety, so that's, I guess, one that we're all familiar with. C++ doesn't prevent us from taking any index and then indexing into an array or a vector without bounds checking, right? So we have stdvector.add, which does the bounds check, but the default is the operator square bracket, which doesn't do that. And so a lot of vulnerabilities are kind of variations of this, right? And then there's lifetime safety, which is basically accessing an object that isn't there because either it has been destroyed, or it's not been created yet, or it just was never there in the first place. One example is returning reference to stack variable that then doesn't exist anymore because it goes out of a scope. You can have a pointer to something that you deallocate, so that's a use after free. Of course, nobody would write it like this, but the same pattern occurs, a kind of more complicated code. You can also straight up the reference in null pointer. Just forget the null pointer check, right? You can, use an object after move. So this is an interesting one, right? Because you actually keep like a kind of a reference to an element that then isn't there anymore. And here's an interesting one. So here we're mutating a vector as we are traversing it, and then at some point pushback might reallocate the whole buffer, and then again you're indexing into memory that just isn't there anymore because it's been reallocated. And so there's only really two ways to guarantee lifetime safety and not have these kinds of bugs, right? So you can either track the lifetime of all objects globally, and then you end up with a garbage collector, which obviously has performance implications. Or you can do static analysis. This is what Rust does, right? But it's borrow checker. You can statically enforce certain properties, like you cannot have a reference to an object before it's created or after it's destroyed. You can just not write this, right? The compiler is going to bark at you. Or the other really important property of the Rust borrow checker is that you can only ever have one mutable reference to an object and no other references, or multiple non-mutable references and no other references. So you can never have two mutable references to the same object, or one mutable and one non-mutable reference to the same object. You can just not write this in Rust, right? Which restricts programming quite significantly, right? So there's things like a doubly linked list, which you cannot write in safe Rust. It's not possible. You have to drop down to unsafe Rust, where you can do all the ugly stuff again to write this algorithm, right? So there are trade-offs of performance, expressivity, etc., etc. In Rust, you can also not have naked iterators the way you can have them in C++. You can also you can operate in ranges, but you cannot have just an iterator to something. And then there's initialization safety, and I also have a talk just about this. It's this thing, right, where you just use an uninitialized scalar variable. And here's a slightly more subtle version of this. You have a struct which you initialize, but because of alignment rules, there are some padding bits in between which you don't initialize. And then you memcopy the whole thing, and then the bits that you haven't initialized, maybe there's something in there, like your password, right, which just has been copied out from, a safe part of your program to an unsafe part of your program. This is exactly how these vulnerabilities work. And so, you can obviously prevent this by forcing all variables to be initialized, but again, that comes with a trade-off. And so then we come to thread safety. And in C++, nothing prevents you from writing a program like this, where you have, a thread modifying a variable and another thread, like the main thread in this case, modifying the same variable. Well, you probably wouldn't write that, but something that people do write in audio, for example, right? So you have a synthesizer which has a volume knob which you can turn, right? So there is a GUI thread. Whenever you turn the knob, there's a callback that sets the gain. And then there's a process method that uses the gain to actually modify the audio signal, except that's going to be called from a different thread. It's going to be called from the audio processing thread. And then you get a race condition, right? So some people fix this by writing volatile. It kind of works, at least in x86, but it's of course also undefined behavior. You should write atomic, or if it's too big to fit into an atomic in a lock-free way, then you should use mutexes, etc., 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 right? And so again, here the trade-off is that, for example, Rust doesn't let us do that, but then it also doesn't let us write certain other things which might be useful. Almost there, arithmetic safety. We already talked about signed integer overflow, so unsigned integer overflow is okay. It might be incorrect, but it's not UB, but signed integer overflow is UB. And it leads to really interesting consequences. So here's an example that I found where you're going to get overflow here eventually, right? If the compiler just leaves the code as it is, but the compiler optimizes based on the assumption that overflow cannot happen. And so what it can do is it can move this multiplication out of the loop, right? It's an optimization which is equivalent if you assume that overflow can never happen. But then if you assume that an overflow can never happen, then this can never be false. And then the compiler just optimizes that to true, and you get an infinite loop, right? So that's how undefined behavior, that's the kind of stuff that undefined behavior can do. And so how do other languages do this? Well, in Rust, in debug, you're going to get a panic if there's an overflow, so stuff is tracked at runtime, right? In release, it's going to wrap, right? So you get like wrapping behavior. So you're almost certainly going to get an incorrect result. So you're not going to be correct, but you're not going to get UB, okay? Which is safe. Not necessarily correct, but safe.
Sorry, quick question. Does that
Yes.
mean Rust will never perform this optimization?
No. You can try and devise a benchmark that proves that it's slower than in C++. I'm curious whether you can prove that. I don't know.
It seems like you should be able to prove that.
I don't know. Maybe, maybe not. It's interesting that actually hardware can do this. Hardware can keep track of. The reason I don't think it's going to be slower is that the way integer math actually works in CPUs is that they have these overflow registers, right? So the hardware does keep track of overflows for no extra cost. It's just that the C++ compiler throws this information away to get these optimizations. So yeah, it's interesting. Somebody should do this benchmark. And so as we said, unsigned integer overflow is not UB, but often is not correct. And so we have a couple more types of UB in the language, which kind of we can call miscellaneous. And probably the most significant out of these is that an infinite loop in C++ is UB. And that is actually great if you want to watch a hardcore talk about concurrency. Watch this one, it's great. It talks about why this is a good property because it allows the compiler to reason about threads in certain ways. It also allows the compiler to do optimizations like this. Let's say you have a loop over some linked list, and then you increment a global counter in there. And then you have another loop over the same linked list, and you increment another global counter. The compiler can reason about the first loop. Well, so the rule is an infinite loop is UB unless it does something observable, like writing to a volatile variable or to an atomic variable or doing some input or output, like cout or something like this. And if it doesn't do any of those things and it just keeps looping, then that's UB, right? So the compiler can assume that the first loop is not going to be an infinite loop. So it can assume that the linked list is not going to be closed, because that would be UB. So it can just merge these two loops, right? So you get these optimizations. There's actually two kinds of UB. So the standard doesn't say this. The standard just says there's UB, but like in practice we can distinguish between language UB and library UB. And so library UB is this thing where you have a function in the library and it says if you violate this precondition you get UB. For example, vector operator square bracket. If you give it an index that's out of bound, that's UB. But kind of that's library UB, right? Like the library spec says it's UB. But then if you actually implement it, then eventually you hit language UB, and we also call them soft UB and hard UB. And when you actually implement the function, you might hit hard UB, or language UB, you actually hit an instruction that does something that's UB. And so some functions, they have library UB, but they don't have language UB, right? They have some kind of hardening in there. Like, for example, you can always clamp the index to a valid value, which is also UB, but it's not hard UB in the sense that you're not doing anything that's language UB. Right. So the obvious problem is that in C++ we don't have any of these safeties, right, as we saw. Like in languages like Java or Rust, we seem to have all of them, right? So in Java or Rust, you can't have a variable that's uninitialized. You can't do type punning. You can't, like ranges are always bound checked in Rust and in Java and many other languages. So when we talk about memory safe languages, it means that we have all of these safeties, and in C++ we have none of them, okay? So we have ways to program in C++ that give us these, right? By following coding standards, by writing tests, etc., etc. But the language doesn't give us these, right? So we can't shoot ourselves in the foot. And so what should we do? And again, as everything, it's a spectrum, right? And some people go as far as say, we need to rewrite everything in Rust to make sure that we don't have any of these vulnerabilities, and other people just don't care, right? And most people are probably somewhere in between. So yes, rewriting everything in Rust is great if you can afford it. It's a massive cost, obviously, but if you need that absolute guarantee that you're not going to have out-of-bounds access, you can rewrite your whole tech stack in Rust, and if you can afford that, that's good for you. But, I mean, you're still going to have unsafe Rust in there, right? Because, as I said, you can't do certain things in safe Rust, like a doubly linked list. And even if you only use safe Rust, at some point you do have to call into existing C and C++ code, right? You have an operating system. You will eventually call into the operating system to call malloc or something like this. There was a delightful discussion somewhere on a Rust forum about environment variables. How do you get the value of an environment variable in Rust? And it turns out that the syscall for getting an environment variable is inherently racy. There's like a race condition in there, which is like in the Linux API or whatever. So there's just no way to not have that, right? So you can only call it from unsafe Rust. And then you need to have some kind of safe abstraction on top, right? But you have to come up with that. Like the language is not going to give you that. So we always have this problem of calling into legacy code, which there just isn't any way around that. Well, what about tooling? Well, we have static analyzers, which are really, really good at nowadays at capturing a lot of the stuff, especially the lifetime stuff. We have sanitizers, right? We have UBSAN, address SAN, thread SAN. They don't capture everything, but they capture a lot of stuff. The problem with them is that you can't use them in production, right? You use them on a special build, which is not the build that you run in production, because they're slow. They impact performance. We have coding guidelines, core guidelines. A lot of safety-critical code uses MISRA, which is another set of guidelines, and there's others. There's AutoSAR, et cetera, and there's static analyzers that are designed for specifically these coding guidelines as well. And then there's other engineering practices like code reviews, right? If you have coding guidelines, have code reviews where somebody has to sign off that you followed the coding guidelines, right? Write tests. We have the whole testing pyramid, unit tests, integration tests, et cetera, fuzzers. So I had a conversation with somebody who works in a safety-critical application, and he said that, if you really follow all of the stuff, they don't really have any reason to move on from C++. Like, they can write code that is sufficiently safe. Like, they do have problems sometimes, but they don't have any need to move away from C++ and rewrite everything in Rust, because this package basically works very well for them. There's other opinions. Like, here's another very interesting article, how SQLite is tested, and they have a very extensive kind of testing strategy, which I found very impressive. And this I found particularly impressive. They said that static analysis has actually not been helpful in finding bugs. So it does find bugs, but more bugs like it doesn't find, and actually it finds things that aren't bugs, and then they introduce bugs when they have to modify the code in such a way that it passes the static analyzer, right? So I found that interesting.
On this list, you mentioned tooling, but what about sort of simple things as enabling in the standard lib, boundary checking? There is, at least for GCC, this mode where you can do that, and that will capture a lot of bugs.
Yes.
And
yes.
it's very simple.
Yes.
We use it all the time.
Right. Yeah.
We have very little memory issues. If you do it, plain a search that are on in debug mode, boundary check arrays, and so on.
Right. So you can have a safe mode in your standard library. Yes, that enables these asserts.
You compile and do auto test in debug mode with the boundary checking on. Then in release you get rid of them, but you are capturing a lot by doing that.
It's a little bit similar to the sanitizers, though, right? It's like you run them in some kind of test build, and then you get rid of a lot of bugs, but then that's not exactly the code that you run in production. So yes, they're very helpful. I'm not saying they're not helpful. And I guess this is another thing like that, which I will add. Thank you very much for the comment.
A brief comment also about my list. I do a fair amount of Rust at my day job.
Yeah.
You need all of this in Rust also. Like, you can't ignore it.
So the comment is that you need all of this in Rust also. So that was a good point. But what I found impressive is that somebody who works on a safety-critical application in C++ said that if they follow this religiously, and I'm sure they do what you just said as well, about the kind of safe standard library build, then they're basically okay. They don't have any business need to move away from C++, right? So I found that interesting. How much time do I have? Because there's more and more questions. I still have a few slides.
Why not go with the slides first?
Okay. I'm totally happy to take more questions, but it's going to mean we're going to sit here longer.
No, then let's make questions from now on to the
As you want.
Let's agree on this.
Okay. So these kind of hardened library modes are very good at capturing this library UB, right? And what about language UB though? So and it seems like there are kind of two categories of language UB, right? Some of it is statically checkable, and the static analyzers find it, and some of it is not statically checkable. For example, if you think about the example of a runtime number which is then used as a bound for an array, that's inherently not statically checkable, right? And so there was a bit of kind of controversy over this article where Bjarne Strustrup declared that Rust safety is not superior to C++. And he was mainly saying that static analysis can help us get rid of most of this. And then there was Patricia on Twitter, who is a safety and security expert, who was saying, well, if these people think that static analysis is going to save everything, they're going to badly out of touch. And I think what they're doing is they're kind of talking past each other. I think what Patricia meant is that a lot of the vulnerabilities that we're seeing is this not statically checkable UB, right? It's like a runtime thing that's then being used for something that causes UB. So runtime value is inherently not statically checkable. However, I think what Bjarne is talking about is about actually evolving the language further. So Patricia was talking about C++ today and how a lot of the vulnerabilities in C++ today are inherently not statically checkable because they're runtime things, which is true. But then what is also true is that we can evolve the language and constrain the language by kind of moving this line down and basically saying, well, let's make more stuff statically checkable, which then the flip side of that is that you're allowing, you're not allowing certain constructs, right? For example, if you have a runtime number that you then use to index into an array, then you could come up with a new language rule saying that you can't do that. The compiler is going to bark at you. It's going to enforce bounds checking in that case. I guess we're done. Okay. Did we hit the time, the hard?
We had this last time when Phil was here, exactly the same.
Okay.
Just happens very fast.
I'm just going to keep talking. So something that we can do is we can say, well, something that where we can't statically check that it's not UB, it's just not allowed anymore, right? But then either we get potentially performance regressions, like with the bounds checking, or we break existing code, which is bad. We don't want to do that in C++, or both, right? So it's all about these trade-offs. And let's see if this switches on again. Do you want me to? I can maybe pull the cable out and back in.
Because we have nothing on the...
Oh, the projector is just off, yeah. Okay.
There's a fan that needs to cool down and cool up and everything.
Yes. Okay, well. Somebody know a joke?
There we go.
All right. Not very safe. So yeah, we can talk about the language today. We can also talk about evolving the language further, right? So we can say, well, we're going to move this line down, right? And this is what Rust is doing. Rust is moving it all the way down to the point where you can reason about all UB at compile time and just not make it not compile, right? This is kind of the Rust strategy. So it seems like we have a chance of improving the situation by actually changing and evolving the language specification. So what is the C++ committee doing about this? Well, we have a direction group on the committee, and they published a paper Bjarne also published a paper. I would say that both of these papers in a wider like programming community were not very well received, to put it mildly. I think it's a little bit misunderstood though. So Bjarne's work is actually interesting. So he proposes this kind of, he says, cocktail of three things. So he says, well, we should really be kind of using coding guidelines, and then we should have static analysis that that enforces these coding guidelines. And global static analysis doesn't really scale, but he says, well, forget about that. Let's do local static analysis. And this is kind of what we need, right? If you can have a static analyzer that can reason about, a reference to something escaping the scope of that object, and then where it could be no longer alive, then that static analysis can tell you this is potentially unsafe. Don't do that, right? A little bit like what Rust actually does, right? And then we can also have library tools which are different from the ones that we have today, where the safety is built in. Like, for example, we have std_span, which initially was proposed as always being bounce checked. And then the committee said, well, but we want performance, so they made the default span non-bounce checked. But we can have another span which is always bounce checked, right? This is what Bjarne is proposing. Like, they have this GSL, the guideline support library, and they have all of these kind of safe by default library features, right? And so the other thing that's really important is he says we could have profiles, right? So we can compile the same piece of code with the performance profile, which is probably very similar to today's release build, but then also with the safety profile, where you have all of these static checks enabled, and where if you have a reference to a local stack variable that gets returned, then the static analysis will not let you compile that code, right? And so the idea is that a piece of C++ code will mean the same in all of these profiles, but in some of these profiles it might not compile. So that might break code if you're using that profile, right? So one thing that's, I think, really important about this is that it doesn't actually aim to eliminate OUB, and it also doesn't actually say that static analysis is the answer to everything. It just says that it can help us get the number of bugs down. So I think it is an interesting direction. It's obviously a lot of work. It hasn't really been proven yet, as far as I can tell, that this is actually going to work. So I guess we just need to wait and see. There's other work on the committee going on. There was this paper also from December. So a lot of work has happened kind of over the last half a year here. And this is about basically adding lifetime annotations. There's a claim that that doesn't scale. I don't know that myself. So again, we need to wait and see how this develops, and whether people who try and use these kind of proposals are successful or not. And there's something that I call the salami tactic. This is something that exists in German as a saying, like you solve a problem one piece at a time. I don't know if Swedish has the same idiom. Maybe it does. Yes, so kind of the idea is that you take a particular case of UB that we can reason about, and we focus on UB that's already statically provable today in C++. And then we can just say, we redefine what it does to make it not UB. Right? So, and we look at this case by case, and we do it only when the trade-offs are favorable. And there are all these trade-offs. It depends on the case, right? So the committee has been doing this for a while now. So for example, in C++20, we got implicit lifetime objects, where something like was always valid in C, but was undefined behavior in C++, right? Where you have a chunk of memory which comes from malloc, or maybe somewhere from the network, or some kind of binary file or whatever. And then we just cast it to a object of type X, but we never constructed an object of X, right? So that's a violation of the object model. But then in C++20, we have this thing called implicit lifetime objects, where the very act of casting it to a pointer to X will actually make it so that this object exists, right? Notionally. So it's no longer UB. Here's another example. This is something we did in C++23, the upcoming standard. We had this problem with that in range-based for loops. It was always okay to loop over a temporary variable, but then if we loop over something that is a temporary variable coming from that temporary variable, then that was UB, because of weird rules of like how an temporary object doesn't outlive this expression there. And we changed the rules in C++23 saying that all temporary objects that are created here during this right-hand side of the for loop, they actually live for the duration of the whole for loop, right? So that slightly changes the semantics. There is like a weird case where it like locks and mutex, and then you get actually different behavior, but it seems like nobody's actually using this kind of stuff, so it felt like there's like 1,000,000 times more code that it's going to fix than code that it's going to break, so the trade-off was favorable, so we did that. And for C++26, we're looking at more proposals, right? So there's one by JF Bastian who says, well, why don't we just zero initialize everything by default, right? And then that's not UB anymore. And then if that's a problem for you because of performance, then we introduce an attribute there saying, no, this is actually uninitialized, right? So this is a bit more controversial, right? So there's several trade-offs there. If you introduce a new attribute, we introduce complexity, right? We potentially introduce performance regressions, although he says that in most cases it's actually not that relevant, or not as relevant as you might think. Another thing that actually can mask bugs, right? So this is a case of like prioritizing safety over correctness, right? So if you say int I, that's always 0 by default. 0 might not be the correct value. Like for example, in Linux, I think the UID equals 0 it always means that it's the root user, so it's actually the worst possible default value you could use.
The OpenSSL bug from a couple of years ago. They relied on an undefined value to see the key.
Yes.
Someone fixed it, they put equals 0, and they destroyed the key space to like 6,000 possibility that you could brute force.
Huh, that's interesting. You need to talk about, I want to know more about this, thank you. So I'm not sure if you're going to adopt this. I think it's quite controversial, but you know.
What if you do that uninitialized on something that has a constructor?
It's just a proposal. At this point, I think it would be a compiler error, but we haven't talked about the semantics of that attribute yet. It's just a proposal at this point. Here's another one. Let's make trivial infinite loops not undefined behavior anymore. And again, there's a trade-off, right? So it disables certain optimizations. And then one thing that we're very actively working on in the committee actually right now is to do something about this library UB, right? Where if you say, okay, well, calling a function, a library function, with an invalid value, that's UB. Well, a lot of libraries, like you said, the standard library and probably lots of third-party libraries have checks in there, like asserts that you can enable, right, where it catches that. Let's standardize that. So we're talking about, we're working very actively on a feature called contracts, which we hope to get into C++26, where you have a standard way of expressing these preconditions, right? And you can say, it's a precondition of this function that index is smaller than size. And then it's better than assert because it's type checked. You know, like you can install your own violation handler. It can hook into all the tools and IDEs and everything. So it's just a lot better than custom assert macros. So that's going to hopefully deal with library UB in a very nice way. And so that's what we're doing in the committee. And so, okay, I'm going to wrap up very soon, but let me just have a couple more words about what's happening outside of the committee. Couldn't we just add a borrow checker to C++? So people have looked into this. And everybody who's looked into this, as far as I know, has failed, has not figured out how to do it. Here is one effort by Google, who obviously have a lot of resources. And they tried. And they figured out, with today's C++, basically, we can't do it because the language just doesn't, it's not constructed in the same way that it allows us to do this, right? So for example, having a raw pointer to something is bad, right? That pointer can dangle. We don't want that. We have a safe alternative in C++. We have unique pointer, right? Unique pointer is great. It's safe, except parts of its API are not safe, right? So for example, it has a function .release, which releases the ownership and gives you a raw pointer back. And then if you don't delete that manually, you have a memory leak. So we can say, well, let's just remove the unsafe bits. Let's just have a unique pointer which doesn't have the release method. Or like the release, if you call release, that's not going to compile in like a safety profile mode, right? But it turns out that it's a lot deeper than this. It's actually about how the language is constructed. So okay, let's ban this. We still want to be able to do this, right? Because without this, we can't do anything. We need to be able to call a member function on this object. But how does it work? It works by calling the dereference operator. The dereference operator returns a reference to the object, right? So if you can do this, just because of the way operators work in C++, you will always also be able to do this. And then you have your raw reference to the object, which can become dangling. And so you cannot fix this without fundamentally changing how the language works, right? And that's why it works in Rust, but it doesn't work in C++. So you will have to fundamentally change the semantics of C++ to make something like the Rust borrow checker work. Sean Baxter, who works on the Circle compiler, which is kind of has lots of extensions on top of C++, is claiming that he's done it, or he's like almost there. So I wish him good luck. I really want to see how it works when it comes out. But I haven't seen it yet. So as far as I know, nobody has actually succeeded yet in implementing something like this. So another effort that I briefly want to mention is CPP2. I'm sure some of you have heard about this. This is Herb Sutter's pet project. CPP2 is like a new syntax for C++, right? Which kind of doesn't let you express a lot of these unsafe things, but then actually compiles down to normal C++, right? So it's like just an alternative syntax for C++, like a new syntax. He calls it a new skin, but not really a new language, which doesn't let you, for example, write uninitialized variables and stuff like that. And then, here's just another example. So Apple had this thing which they did for iBoot, which is the software that boots up your iPhone, where they modified the C language and the C compiler boot chain to make C memory safe. Actually, really interesting. Somebody reverse engineered this. It's a fascinating blog post about how this works. And then people are rewriting stuff in Rust, right? So this is a fascinating article from Google. So Google is introducing more and more memory-safe languages in Android, and they're seeing that the number of vulnerabilities is going down with every release, because the number of memory-safe languages the amount of memory-safe languages is going up, right? And so these are actually correlated. The less code they write in memory unsafe languages, the less memory safety vulnerabilities they get. Of course, Google, has a lot of money, so there is another trade-off here: safety versus cost. So not everybody will be able to afford to do this, right? So I'm at the end finally. Thank you for bearing with me. I think I overran by like 10 minutes. I would say C++ is not dead. Everybody who says it's an existential threat for C++, I think is overstating things a little bit. There are so many billion lines of C++ code out there that are not going anywhere, that I don't think we're going to be out of jobs anytime soon. Maybe this whole thing is just a PR problem, and I think kind of yes and no. It's like, it's not as black and white, right, that we have memory safe and memory unsafe languages, and the memory unsafe are super bad, and the memory safe, they don't have any vulnerabilities at all. It's not like this. It's kind of more like certain types of vulnerabilities you cannot get in certain languages, so you have more of them, so maybe that's a problem, right? It highly depends on the domain. I think we can mitigate a lot of that by using, good tools, good engineering practice, good libraries. But maybe abandoning C++ is the right trade-off for you, and there's probably nothing wrong with that either. And I do think the committee should do more, and we are doing stuff, but it will take time because the committee is working very slowly, and that is a problem. And I think what the committee should also be doing is it should communicate the strategy a lot better, because right now we just have these like piecemeal proposals. We don't have anything to say, okay, there's all this stuff going on, and here's our long-term strategy, how we can address this. And we're not going to make C++ a completely memory-safe language, because then it's not going to be C++ anymore. But we are going to do something to like bring the number down, right? And so I hope that the committee can come up with some kind of strategy paper that convinces us that C++ is not as bad as people make it sound. And with that, I'm done. Thank you for listening. So, can I make two very quick announcements? Number one is I started a user group in Helsinki. I moved to Helsinki 5 months ago. I was shocked to learn that they have plenty of C++ developers, but no user group. User groups are amazing, right? So I started a new one. We have a Twitter that you can follow. We have a meetup.com page, meetup.com/CPP Helsinki. It's another Nordic country, so maybe somebody knows somebody in the area. We really look for sponsors. We haven't actually had a meetup yet because I couldn't find a sponsor who could sponsor a room like this. So if anybody knows a company in Finland who would have something like this and who would want to host a bunch of C++ developers in Helsinki, that would be amazing. please get in touch with me. And the other thing is that I'm doing a little survey about C++ and undefined behavior for the version of this talk that I'm going to be doing at CPP on C. And it consists of 3 very simple questions, and one of them is optional. So it's really just 2, completely anonymous. I'm not collecting any emails or anything. It takes 2 minutes to answer this. And then I'm going to reveal the results at the CPP on C version of this talk. Please go to timur.audio/survey or this QR code, and please help me out, answer the questions. I'm collecting data about how dead C++ actually is, and you really only have to answer these 2.5 very simple questions, and that would be amazing. And with that, I'm actually done. Thank you very much.